hard to talk after such a remarkable sequence of talks. Wiping off darkness in our understanding the dark side of gravity theory and particle physics. And especially if you're going to talk about certain things that are kind of obsolete now. But, well, you know, the fact that this is an obsolete subject is actually reflected in the title of this talk that was, I believe, kind of truncated in the schedule, in the program of the conference, as it should be. Because this talk is nothing but an attempt to remind you about a very old paper by Sidney Coleman that was written down in the years of the triumph of Euclidean quantum gravity. And this paper was basically the main goal. It was focused on the attempt to completely eradicate any single trace of the cosmological constant. Now, but now the situation has changed, and we know very well that we have to explain the mechanism of dark energy in terms of either fundamental or some other type of cosmological constant behavior in the present-day universe. And so, well, it is interesting that Euclidean quantum gravity gives certain hints of how this can be done. And now I would say Euclidean quantum gravity is a lame duck in the modern quantum gravity and quantum field theory, particle theory, and cosmology. After its summit sometimes in early and middle 80s, in the form of the cosmological wave function, in the form of the baby universe boom, black hole thermodynamics. Then the interest in this theory gradually declined, especially in the cosmological context, where the concept of initial conditions for the universe actually has been superseded by the concept of stochastic inflation. So Euclidean quantum gravity could not stand the burden of such problems as the indefiniteness of the Euclidean gravitational action, as what I call the infrared catastrophe of small cosmological constant, which manifests itself in the following very simple property. If you consider the hard-copying, no boundary wave function of the universe, then it turns out that the creation of the infinitely big universe is infinitely more probable than the creation of any finite-sized one. And, well, this infrared catastrophe situation actually has led to what is called cosmology debate of the no boundary versus tunneling proposals for the cosmological constant. And I would say that for any serious physicist, ad hoc inversion of the sign in the exponential of this expression, as it was suggested in the framework of the tunneling proposal, is nothing but a kind of visual thinking. So in view of all these drawbacks, I would say that it is hard to believe that the recently suggested Euclidean quantum gravity density matrix of the universe can actually serve as a viable candidate for the initial state of the gravitational field and the system as a whole, even despite the fact that it suggests a very interesting mechanism of elimination of the infrared catastrophe of small lambda. It suggests the ensemble of universes in a limited range of the cosmological constant, both bounded, both in the infrared and in the ultraviolet. And in this sense, it actually suggests, directly or indirectly, suggests a very interesting selection mechanism, potentially interesting mechanism, selection mechanism for the landscape of string vacua. So these results have been obtained about a year ago in the work, in the collaboration with my long-term co-author, Alexander Kamenchik. And the goal of my talk today would be basically to justify these results from first principles, but not of Euclidean quantum gravity, which nobody knows what is it really, but from first principles of Lorentzian quantum gravity. You don't have to mix this abbreviation LQG. You don't have to mix it up with loop quantum gravity. I will be talking about quantum gravity as effective theory of gravitational field in the sense of determinative, so to say, Feynman diagrammatic technique, in the sense of the usual formulation in terms of the path integral, which is considered, I think, still considered to be the very powerful tool for constructing unitary S matrix in scattering and other phenomena in particle physics. So basically what I will do, that's the short plan of my talk. First I will just briefly recapitulate the results obtained about a year ago in the frame of Euclidean quantum gravity and show how the effects of the conformal anomaly in radiation and cosmology lead to such a bounded, limited both in the ultraviolet and the infrared domains, the limited ensemble range of the cosmological constant. Then I will show actually that the same, then I will go over to the construction of the density matrix rather than in Lorentzian quantum gravity, and actually will show that this density matrix will describe a microcanonical ensemble in the theory of spatially closed cosmology. And this ensemble will be rather peculiar in contrast to usual systems which do not satisfy, which are not the constraint systems. This ensemble will actually realize a rather interesting idea that it will be a sum over everything. It will realize the idea of ultimate equipartition when actually the distribution of initial conditions for the system will be actually smeared with unit weight over entire space of true physical variables of the system. And then I will show how actually the calculation of this strange, it would seem vacuous, so to say, equipartition actually leads to a very interesting result, that in terms of the observable physical quantities, like for geometry of space-time, this equipartition is actually peaked about those instantons that were obtained in the framework of the Euclidean quantum gravity and belonging, spanning this finite range of the cosmological constant. Well, I will show how actually the integration over the mini-superspace will perform this effective selection of thermal instantons and will endow them with the thermal nature. And finally, I will briefly consider the mechanism, how this picture actually contains not only the mechanism for the initial value of the cosmological constant in the early universe, but also at the level, at the late stages of its evolution in the form of the cosmological acceleration. And I will give some, at least this is just an idea, and there is a very long way to go, but how this mechanism can actually generate, solve also the hierarchy problem for the present day value of the dark energy. Okay, so let me briefly consider the idea of that old work. That idea is based on the assumption that there is no any compulsion to consider the system of the gravitational field, the whole universe, as a pure state, at the initial stage of its evolution. It is up to nature actually to decide what is more preferable. Either it is a pure state, like the vacuum state of the no boundary Hart-Hawking type, or it is actually a density matrix. And at the dynamical level, this question should be resolved as a result of the calculation of the corresponding statistical sum. So the idea, graphically, the idea looks very simple. This is the graphical representation of the pure quantum state, say, of hard-Hawking type. This is Lorentzian space-time Euclidean from the Euclidean hemisphere, which, so to say, realizes the idea of inflation, of the creation of the universe from nothing. That is, from the point which is the pole of this Euclidean hemisphere. Well, apparently, the same state can be reformulated in terms of the density matrix, which is just a factorized density matrix, which is a direct product of psi and psi star. And graphically, it is represented as a union of such two manifolds, which they are disjoint, and they have two disjoint pieces of the boundary associated with two arguments of the density matrix. Thirdly, if we go over from the notion of this pure state density matrix to the generic situation when the density matrix is not factorizable, then certainly there is a bridge which interpolates between these two manifolds and establishes the correlations, density matrix correlations between the observable sitting here and here. Now, let us present the same idea in a quantitative manner. So the density matrix in Euclidean quantum gravity is determined by the Euclidean path integral over gravitational matter fields, interpolating between the given fields at this boundary and this boundary according to this simple prescription. And the normalization of the density matrix to unity immediately gives the expression for the statistical sum or for Euclidean effective action of the system in the form of such an integration over periodic configurations. And certainly this periodicity of this configuration, which follows from this trace, it is just graphically can be represented as a compactifying this tubular space-time to the toroidal one. Now,
sorry, is this a thermal state? You're writing a thermal state?
Well, of course, but we don't know yet whether it is thermal or not. It is mixed. It's a mixture. And whether it will have thermal properties, this is a question of quantum calculation. But so to say, at least, well, we would anticipate that we'll have something like a thermal nature. But you see, this torus, it is not static. So we don't have to speak about equilibrium thermodynamics. And in this respect, it differs from the usual thermal ensemble with fixed temperature. Okay, I will talk a little bit about this later in more detail. So the next step is very simple. We just consider mini superspace sector of this theory, and on top of it, which is described by the lapse function and the scale factor of the FRW metric, and we put on top of it all the possible spatially inhomogeneous fields, including also metric perturbations. And then the path integral for the statistical sum can actually be decomposed into the composition of two nested integrals. So the interior integration gives the effective action of these quantum fields on top of this mini superspace background, and we have the integration over this mini superspace fields of this effective action gamma E of A and N. So it's quantum effective action of phi on the mini superspace background. Now let us make the principal assumption that conformally invariant fields, quantum conformally invariant fields, are outnumbering. They outnumber all the other non-conformal fields. And under this assumption, the effective action can be exactly calculable. And the result of this calculation is given here. The calculation of the effective action for free but conformally coupled to gravity fields can be performed with the aid of the conformal anomaly method. And the result of this calculation is here. I repeat that this is exact action. So nothing has been actually dropped here. All the other corrections due to conformally non-invariant fields, they play the role of perturbations which we just disregard in the in the 1 over n expansion, where n is a number of quantum conformal fields. So this is the structure of the effective action. It includes classical part, the contribution of conformal anomaly, vacuum Casimir energy, And what is important, there is a coefficient here, B. This is just a coefficient of the topological Gauss-Bonnet term in the total conformal anomaly of the system. But apart from the local contribution to the action, we also have a non-local thermal part, which is just a typical free energy sum of the system. This is a typical sum over field oscillators with frequencies omega on a three-dimensional sphere. Maybe I forgot to tell you that I am considering the simplest topology for a spatially closed system. This is just a three-dimensional sphere, and the scale factor which describes its size. So what is important that the role of inverse temperature here, eta, is played by the conformal time, which is a non-local functional of both A and N, lapse and scale factor, and the integration over the Euclidean time is along the perimeter, along the circumferences of the toroidal space-time.
So
okay.
Temperature is because of periodicity condition.
Well, it's not yet a temperature, it's effectively a temperature, but of course it comes from periodicity. But the period of this temperature is not an input parameter, it's not fixed by hand. As we will see now, this effective temperature is a result of the solution of effective equations of motion for this effective action. So we just write down this effective equation. This is a modified Friedmann equation, which is modified by the presence of the conformal anomaly term and also by the presence of the radiation type term. And the radiation here is for obvious reasons. This is a quasi-thermal situation. This is a mixed state which is just encoded in the very definition of the density matrix. But the amount of this radiation, this constant C, is not arbitrary. It is actually given in terms of the vacuum Casimir energy of quantum fields plus the contribution of thermal excitations. And this contribution of thermal excitation, this is a non-local functional, as I said, of the history of the scale factor as a function of Euclidean time. So this is a closed back reaction system, and it can actually be analyzed in a self-consistent manner. And the result of this analysis is very interesting. It turns out that the solutions of this system really exist, and they represent the so-called garlands. This means these are toroidal instantons, but the cosmological factor, the scale factor of this instanton, the width of this tube, is not constant function. This is a non-trivial function of time, which can actually oscillate between the minimum and maximum values. And the number of such oscillations, we call it just the number of folds in this instanton, in this garland. So in a sense, these instantons at the three-level approximation were suggested many years ago by Halliwell Myers, by Fisher, Morgan, and Polchinski. And they're quite interesting in that the role of radiation in quantum cosmology was pulled from oblivion by Henry Time and his co-authors, who actually played a very important role in the motivation for this work.
Andrei, why you add radiation?
Pardon me?
Why did you add radiation?
Radiation naturally arises there. This is just intrinsic element. Nothing has been put by hand. You have vacuum and you have excited states over this vacuum. And these excited states, they are distributed according to this rule. This is just the result of calculating effective action and writing down the effective equation.
So C divided by A force?
Well, yes, it's effectively some radiation density, which is 1 over A to the fourth behavior.
Because of periodicity.
Of course, periodicity. Yeah. It's not vacuum. That's important. And now we will see whether this statistical sum will be dominated either by the system in which C is roughly 0, no radiation, or not. And the result is very interesting. So we get the set of such Garland-type instantons which saturate all possible saddle points of the Euclidean effective action. And it is interesting, first of all, these saddle points exist only in the limited range of the cosmological constant lambda. Well, lambda parameterized in terms of h squared. This is just the cosmological constant that was input in the classical part of the Einstein-Hilbert action. So we see it's between maximum and minimum values. It's the bounded range of the cosmological constant. And it is interesting how they arise here in this picture. It looks like this. If we analyze a set of solutions in the two-dimensional plane of the cosmological constant and the constant c, the amount of radiation, then they exist in such a curvilinear wedge, which is bounded from above by this cusp point. And well, that's the boundary, a lower bound and higher upper hyperbolic boundary, which I don't have time to discuss how do they arise, but all this is written here. And these solutions, they form one-parameter families. So K, one-fold family, is shown here. It interpolates between the upper and lower boundary. What is important is that the lowest value of the cosmological constant is non-zero, it is positive. Then this is K2, K3, K4, and so on, up to K infinity. So there is a sequence of one-parameter families of such solutions, which actually converges at this upper boundary, which this upper boundary forms a new quantum gravity scaling theory. It is given in terms of the coefficient of the conformal anomaly. And this is essential non-perturbative effect, new quantum gravity scale. Now, what is important? That it turns out that hard-Hawking instantons corresponding to pure vacuum state are completely ruled out in this picture, because one can show that for any positive lambda, well, negative lambdas are also do not enter the game, but for any lambda, they are completely eliminated due to the same anomaly effect. It turns out that the Euclidean gravitational action with the contribution of anomaly for such instantons turns out to be positive and infinite. So they are all completely suppressed to zero. And there is also a very interesting scaling behavior. This range actually shrinks as 1 over n when we increase the number of quantum fields, conformal quantum fields in the game. So this is a very good 1 over n approximation. You see, which looks maybe anti-intuitive. The more fields we have here, we don't have a bigger curvatures, but we go over into lower energy domain. So that semi-classical approximation becomes more and more justified. Okay, so that was the picture of Euclidean quantum gravity, but nobody cares. What does it mean? Nobody understands really. To what an extent one can trust this Euclidean quantum gravity? Because this is something not real. This is a handmade construction which does not really justify lots of hopes that were imposed on this construction in early 80s. So now I would show that the same conclusions come from Lorentzian quantum gravity, and for this I would construct the density matrix of the Lorentzian quantum gravity in terms of the integral over the phase space of the system with the usual canonical gravitational action. So again, we have the integration over histories interpolating between the two arguments of the density matrix. But what is important, that the range of integration over lapse and shift functions here and mu, it's infinite. Therefore, this expression actually satisfies the system of the well-known, but never really properly used, Wheeler-DeWitt equations, which are just the constraints, gravitational constraints imposed on the coordinate representation of the canonical commutation relations for the coordinates and momenta of the gravitational theory. So from here, it is obvious that this rho, this is two-point quantity here, it actually can be represented, it is a sort of a delta function. This is an operator, or this is a matrix element of the operator, which can be thought of as a delta function of the constraints. And this is a crucial point for understanding that this density matrix is actually microcanonical density matrix in the gravitational theory, because the simplest analogy is this is an unconstrained system with a conserved Hamiltonian in the microcanonical state with a fixed energy E, which looks as follows. But in spatially closed cosmology, it does not have freely specifiable constants of motion because of spatial closure. The only conserved quantities are the Hamiltonian and momentum constraints, all having a particular value, 0. And therefore, this is a very natural definition for the most generic state, microcanonical state in the gravitational context. We do not have any freely specifiable input parameters here, just nothing. No dimensional quantities except maybe two-dimensional ones, Planckian mass and cosmological constant. So this is the microcanonical statistical sum of the universe. And now we will show that it is really a uniformly distributed with a unit weight integral over entire phase space of true physical degrees of freedom. So this is a sum over everything. Well, this is very simple. So we again construct the statistical sum with this Lorentzian path integral, and then according to the usual well-known rules of Fadeev-Popov gauge fixing procedure, we just perform the transition in this Lorentzian path integral to the physical sector by imposing the gauge conditions, solving the constraints together with these gauge conditions, and going over from initial Q at P to Q physical and P physical. Then this path integral in terms of Q physical and P physical takes a very, very simple form. This is just the usual unitary evolution operator in the physical sector of the system. But what is important, Fadeev-Popov path integral is gauge independent on shell, and this quantity is really on shell. Therefore, it can be calculated for a particular set of gauges which are time independent. And for time independent gauges, because of the spatially closed nature of cosmology, physical Hamiltonian is just 0. Therefore, this factor here is just 1 in the space of physical degrees of freedom. And therefore, what we have, this is just trace of this operator unity, and this is just the integral over entire phase space of physical variables, I repeat, with a unit weight. This is sum over everything. And now let's show that this sum over everything, actually, in terms of the observable quantities, like for geometry, they are really peaked. This integral is peaked about these instantons that I considered before. So, well, the calculations are very simple. We just first integrate over momenta. This is a Gaussian integration. Then again, we perform the same decomposition into mini-superspace and spatially homogeneous field sectors. And then we get, again, the same representation of the full path integral as a nested integrals over quantum fields, and then the integral of mini-superspace sector. And then we consider its saddle point for Lorentzian metrics. And remarkable property. In Lorentzian signature, there are no closed trajectories satisfying periodicity conditions with real values of Lorentzian metric coefficients. But such solutions exist in a weak-rotated Euclidean geometry. And these are exactly those that we obtained there. And actually, this Euclidean rotated path integral obtained by weak rotation from the Lorentzian can be obtained by such a procedure. You just relabel the time variable from Lorentzian to Euclidean, just rotate by I the lapse function. And then the relation between Euclidean objects and Lorentzian objects is like this. But what is important, that now the integration in the Euclidean integral should be run over the imaginary axis of the lapse function. And this is actually the justification of the conformal rotation in Euclidean quantum gravity, because this was used as a trick in order to give certain finite value to the Euclidean path integral, because in the sector of the conformal mode, this integral is not Gaussian. You have not e to the minus x squared, but e to the plus x squared in the exponential. So it was just suggested by hands to rotate the contour of integration. Now we see that this rotation is actually inherited from the correct definition of this path integral in Lorentzian situation. So now what we do...
Can I just ask a question?
Yeah?
What happened now finally to the action You are just now saying some of my opposite, but you still have an exponential factor of the action, or not?
Of course, yes, because in terms of the,
So in that
in
sense,
terms,
it's not
you see, this,
exactly similar to the
this
micro-
Liouville integration over the space of true physical variables, this is a very complicated quantity, because in order to disentangle physical sector from the full gravitational system, this is a great pain, and there is a lot behind.
Yeah, but then you still, if you have still an action, you still have also the cosmological constant as a parameter in the action.
Of course, yeah.
So, okay, yes, it's
Yeah,
not
certainly,
something that you will finally get out, but that is something that you have in your action.
Yeah, of course, yeah. But again, this cosmological constant can again be considered as a composite field like inflaton, and you can again consider this distribution.
Yeah, no, I just wanted to clarify the status.
So what we do now, we just perform the conformal rotation of the Euclidean contour of n according to this recipe that is inherited from Lorentzian theory, and we deform it into the complex plane in order that it would pass through the saddle point, which turns out exactly the same saddle point as we considered before. There is one transparency here explaining that actually the integration over the mini-superspace sector in the vicinity of this saddle point actually does not bring any new radiative corrections, and this is a very simple property. You know very well that this sector does not have true physical degrees of freedom, so that any integrations over these variables will be compensated by the corresponding contribution of the Faddeev-Popov ghosts, and actually that was Raman Sundram was talking about in this context in his previous lecture when he was trying to explain how he wants to check unitarity and the cancellation of these unphysical contributions with the contributions from the ghost sector, but ghost sector in the sense of the Faddeev-Popov, not in the sense of the physical ghosts. So I don't have to explain how it goes on, but roughly speaking, what happens here, I'm sorry. I'm afraid I just pressed the wrong yeah. So this is just we have the integration over conformal mode, the contribution of the Faddeev-Popov ghosts, and one can show how these two functional determinants cancel out, so that the result is just the, so to say, the three-level contribution of a saddle point. But this saddle point of the fast integral already includes the quantum contribution of all physical quantum fields that are in the game. So just, well, maybe 3 more minutes, if you please. I'm sorry for bringing forward my schedule, but it's really a very, very compressed material. So how a dark energy can arise from this picture? It is interesting that if we consider the Lorentzian universes with initial conditions given by this certain point instanton, this will be a correct picture of how Lorentzian evolution arises from this initial statistical ensemble of microcanonical ensemble, which has a quadrithermal nature. So this is just an analytic continuation of that Euclidean effective equation into the complex of the complex time. And it is interesting that at late stages of evolution, the solutions of this equation, they just demonstrate two branches, just like in the DGT model, two branches of expansion with two values of h plus minus Hubble constants, given in terms of the fundamental Hubble constant and the parameter b, which is the coefficient of the conformal anomaly. So certainly we have to assume that this initially fundamental Hubble constant, this is just a composite field, something like in terms of the inflaton or whatever. And therefore, if we input the usual exit from inflation, then there will be a decay of this composite H. This means that one of the branches will just go to a static branch, not expanding at all, and the other branch will undergo eternal quasi-exponential expansion. So there is, you see, that there is even the cosmological acceleration is encoded in this game. But the cosmological acceleration scale is, unfortunately, it is given, you see, roughly by Planckian mass squared over b. And b, this is a topological, the coefficient of the topological term of the quantum anomaly. And roughly speaking, up to a spin coefficient, it is proportional to the number of fields. So what? Is it actually possible to really to match the scale of that scale is the scale of the present-day acceleration? Quite unlikely. But there is an interesting mechanism which I think has never ever been really considered in literature of how there is some tendency, or there is the idea of how this matching can be done. And certainly this uses the idea of extra dimensions. If we believe that this picture is just a low energy field theoretical limit of string theory, then we have to trust, we have to believe that there are extra dimensions. And therefore, the role of the conformal fields in our game, in our picture, is played by either Kaluza-Klein modes or winding modes. And therefore, the number of conformally invariant modes which are approximately massless, that is, they are actually super horizon, that their masses are much smaller than the scale of the expansion of the gravitational four-dimensional background, that this would mean that in the assumption that the extra dimensional size is not a constant, it's not stabilized, and there is no actually compulsion to consider that the stabilization of moduli would always took place. It is maybe stabilized now, but it was not in the early stages of the cosmological evolution. This means that the number of such conformally invariant massless modes, which are either Kaluza-Klein or winding modes, actually depends on the size of this extra dimension. And therefore, we can imagine two possible scenarios, either with the contracting or expanding size of extra dimension, that this number n, in the case of the super horizon Kaluza-Klein modes, it actually grows with the growing size of extra dimension, so that the scale of the cosmological expansion turns out to be inverse proportional to R, and in principle it is indefinitely decreasing. The other scenario, that you have again a growing tower of super horizon winding modes corresponding to the decreasing size of extra dimensions, and in this case you see that again the acceleration scale, the dark energy scale, is again decreasing as a positive power of the extra size. So maybe this could serve as a hint that there is a possibility to generate the dark energy phenomenon now from this picture. And now I'm just finishing. So what we have in the end of the we have density matrix reloaded. We have under a minimum set of assumptions. It's basically an ultimate equipartition in physical phase space in the form of the microcanonical state of closed quantum cosmology. We first have constraining the ensemble of lambda and possibly the landscape of string vacuum. Then we have a new dark energy mechanism transcending the inflationary and matter domination stages as a quasi-equilibrium decay of the initial microcanonical state of the universe. And just to finish my talk, I would say that in addition to a well-known nothing comes from nothing, and against the anticipations of Sidney Coleman that there is nothing rather than something, we can say that something rather than nothing comes from everything. Thank you.
I'm missing in this picture somewhat an essential ingredient for cosmology, namely the entropy production after inflation that should then make an effective transition to a classical behavior. Is that not present at all?
No, the usual evolution, including inflation, particle creation during inflation, formation of CMBR, and then reheating. It is included there. Because you see what happens. Initially, the system had certain amount of radiation, and it also had the cosmological constant in it, of either fundamental or composite nature. Then what happens? It starts expanding. And certainly what happens that this initial primordial amount of radiation, it gets diluted. So at certain stage, the cosmological constant that was from the very beginning, it starts dominating. And it gives rise to the usual inflationary stage of the universe, during which you have all these effects of particle creations of the other sorts, of the other type, as compared to this radiation that is just going to zero. And then their thermalization, reheating, and so on. So this is just a conventional scenario. There is nothing special. And then if this cosmological constant that was from the very beginning is not a fundamental, but if it is just a composite inflaton field, then we have the usual exit from inflation. We have the usual generation of entropy, if you would like to put this kind of scenario in the form of the entropy growth or whatever else. So it is, everything is included. But in certain sense, this is that we are returning to the original idea of Big Bang, that the original universe was hot. But in that picture, it was infinitely hot. Here, it is not. It is hot, but its temperature is not infinite. It is actually bounded from above by the same bound as the cosmological constant is bound. So it's basically a Planckian square divided by the number of conformal multiplets in the system. So it's the same cutoff.
Okay, this